Welcome back. In today's video, we'll talk about applying deep learning models, another term for these being neural networks, in R using the RStudio interflow to keras and TensorFlow. So let's get started. Couple things to note. I'm going to be switching back and forth between RStudio and the slides in this video, so that's why I've chosen to not show the face cam today. So if you were hoping to see my basement, I apologize. I apologize for that. This will also be a little bit longer than some of the last few videos because we have a lot to talk about as far as implementation options with neural networks. So far, most of the models that we've talked about in this class are what we call shallow machine learning models. So we're really only using one or two layers or one or two steps of inputting data, manipulating it to learn the output or learn the target variable. However, in deep learning, we take a multi-layer approach. So we feed data into the model, we do some manipulation of the data, we then continue to work with that manipulated data, remanipulate it, and so on through multiple steps or multiple layers. The most commonly used approach to deep learning in machine learning is neural networks. Since neural networks aren't covered in Introduction to Statistical Learning, I recommend checking out Hands-on Machine Learning with R, Chapter 13. Even for those of you who aren't using R, this book does provide a pretty good hands-on introduction to how these models work. So that's a good place to get started. Okay, so when people say implementing machine learning models, specifically neural network models, a lot of the time that's synonymous in practice with working with TensorFlow. So what is TensorFlow? It's an open source software library for machine learning applications. It was written and developed by the team over at Google, and it's available for anyone to use and work with. So let's take a look at the TensorFlow website. We'll go to, if I could type it in, tensorflow.org. As you can see just from the main page of the site, there are a lot of ways to implement TensorFlow. So there's ways to implement it for training machine learning models. You can insert TensorFlow directly into production. You can work with it in JavaScript for those of you who are familiar with that, but primarily TensorFlow is written and works with Python. One thing to note, for those of you using the latest Python installation, Python 3.8 or later, you will actually need to downgrade in order to work with TensorFlow on your computers. A way to get around that is to use Google Colab. So Google Colab is very similar to RStudio Cloud, just for Python. So that's TensorFlow. TensorFlow kind of goes along with a Python library known as keras. So keras is an open source library for neural networks written in Python. It's part of the core TensorFlow library. So these terms are often synonymous in practice. Keras is probably one of, if not the most developed modeling pieces of software for working with neural networks. There are loads of options available to work with in keras. Now, R doesn't really have a good competitor for keras at this point. There are some R packages for doing neural networks, but not nearly as robust as keras is. However, to address that, the RStudio team has put together an R interface for working with keras. So you can write R-style code, specifically tidyverse-style code, and work directly with keras. So you can interface with this Python library without having to use Python syntax, which for an R developer is fantastic. In order to get started with this, check out keras.rstudio.com. That's the website that we just looked at. It's got some details on installation. Again, a couple things to note. First, you'll need to install the keras package directly from GitHub. So if you've been having some problems with this DevTools library, developer tools, you may want to try to update that first. You'll use the keras library to install keras. This is going to install both keras and TensorFlow. You do need to also have Python installed on your computer for this to work. I will post some links on the on the Blue Line module for interacting with and installing Python. One option, if you are not really into the idea of installing Python on your own computer, is this. I've created inside RStudio Cloud what I'm calling a keras sandbox. So this has Python installed, this has TensorFlow, this has keras, and should be relatively ready to go. If you want access to this RStudio Cloud instance, I can send you access. However, the only way that I can is through email access. So unfortunately, I can't just copy this link and send it to you, but I can send you an access code or I can send you a direct link that's not this HTML. So essentially, if you want access to the RStudio Cloud version, shoot me an email. I'll get you logged in. All right, now that that word vomit is out of me, let's go ahead and continue on. Again, one more reminder. It's really important, it's essential actually, that you need Python 3.5 to 3.7. So if you're using 3.8, you will need to downgrade your installation. So that's why I recommend maybe going the Google Colab route, which I'll provide a link to as well, or the RStudio Cloud route. So as an example, let's start with sort of the classic neural network application, the MNIST database. So the MNIST database, MNIST standing for Modified National Institute of Standards and Technology, was first presented in 1990. So AT&T Bell Lab was reached out to by the US Postal Service, who wanted to create automatic mail sorting machines. So at that time, it wasn't possible to read in handwritten letters and numbers. So AT&T Bell Lab was tasked with creating this. So here's just a small sample of what the handwritten letters look like in digital form. For us, it's fairly straightforward to look at these numbers and recognize which digit they are. However, we've had a lifetime of practice doing this. If we want to, say, quantify certain characteristics of these letters for a computer to look for, that's an entirely different task. So the database that was presented contains 60,000 images in the training dataset and 10,000 images in the testing dataset. So this is a pretty large dataset to work with. The image component is a matrix. Each column of this matrix represents one of the pixels in this image. So each image is a 28 by 28 pixel grid, so there are 784 total pixels in each image. The values in this dataset are integers between 0 and 255 that represent grayscale. The labels component is a vector representing the digit shown in the image. So let's take this code, launch it in RStudio. So here I will show you the R Markdown document that I'm using to create these notes. It's got all of the code directly inside of it. We don't need to install keras. We don't need to do that. We will need to call the library, however. We'll read in this MNIST database. This is a particularly large database, but it still doesn't take very long for R to load it in from the DS Labs, that's Data Science Labs package. We have images and we have labels in both the training and the testing. So what we'll start by doing is just looking at that training data set, and we're going to take those images, put them into a data frame or an input matrix MNIST X, the labels will go into an output database, MNIST-Y. One thing to notice here, I've used multiple instances or multiple occurrences of this $sign. So this $sign just digs deeper into each of these named elements of MNIST. So we'll create an MNIST-X and MNIST-Y. We can take a look at each of these. It will take some time. So here are each column. Each column represents a particular image. Most of the images in the first rows start out white or with zeros, so that's why we're not seeing a lot of values at this point. However, once we start to get toward the center of the image, we'll start to see some values populating. So that's what the input X looks like. The Y, you can take a look at that using the head function. The Y just represents the coded output. So the first digit that's input in this data set is a 5, second is a 0, third is a 4, and so on. So let's go back to the slides and keep working through this example. Before we dig into the architecture of how these neural networks actually work, there are a few requirements that we're going to need. The type of neural network that we're going to work with is what's known as a feed-forward deep neural network. So these essentially work forward with the data. Due to time constraints in the semester, we're not going to be able to do much with other structures of neural networks. These do have a requirement, though. These require all of our feature inputs to be numeric. If you've got categorical features, you'll need to transform those into dummy variables. So columns of zeros and ones indicating membership in a class or not membership for zeros. These are very sensitive to the individual scale of the input features, and that's true for most neural networks. So whenever you're working with a neural network, make sure you're centering and scaling or standardizing your data first. Specifically to keras, the response should be what's known as a one-hot encoded matrix. Essentially, what that means is that the output matrix needs to represent, for categorical variables, a set of dummy variables. So we'll use the function 2_categorical to create this one-hot encoded matrix. Remember, the first observation is a 5. So here in column 6, we're placing a 1. Second observation is a 0. So here in the first column, we're placing a 1. Each of these columns is essentially a dummy variable indicating whether or not we're classifying as that digit. So any ones here are classified as zeros. Any ones here represent an instance that's classified as a 1, classified as a 2, and so on. So that's what one-hot encoding is referring to. In order to standardize these feature values, we know that they range from 0 being white to 255 black. So I'm just going to scale these down to be values between 0 and 1 instead. In this case, it doesn't really make sense to divide by the standard deviation because we want to retain that same variability between the white and black colors. So we want the gray scale to essentially stay gray. So here's what the first image looks like. And we'll go through this code. The first thing that I'm doing here is actually calling a library called the RColor library. This enables me to use specific color palettes in R. I'll create a grid going from 1 to 28 on the x-axis, 1 to 28 on the y-axis, so just essentially building my grid for my pixels. And then I'm going to take each row representing a different image. So I'll take just the first image, first row, and set that to be the colors of my grid. So we've scaled that to be values between 0 and 1. So the lighter colors 0 will be in white, the darker colors 1 will be black. So we can see this image drawn. Now we know the first observation should be a 5. It doesn't really look like it on this representation. That could be because we have the x and y axis switched. In fact, if we rotate this, so flip the x and y axis, we see that 5 shape a little bit better. The other reason why this may not have looked like a 5 to us originally is because we have pixels 1 to 28. Most likely the actual data starts here at the top row going 1 to 28, so that would mean that this image is mirror flipped. Not only that, because it's a default plot and we haven't rescaled it, the grid is not square. So there's a lot of reasons why this 5 may not have originally looked like a 5 when we first plotted it. Image 2 is a 0. So there are things in this data set that are going to be difficult for a human to measure. Things like the angles of a letter. How do we quantify that? Things like the edge, the thickness, whether there's a circle or a straight line. The orientation of these are really important as well for identifying things like letter and number recognition. Because we can't really come up with a good representation of these in a single variable, we build linear combinations of these pixel measurements to create new variables. So the basic architecture of a neural network looks something like this. Our original input features, so each of those pixel darknesses, go into one or more what are called hidden layers. So these hidden layers essentially create linear combinations of each of the input variables. In a simple neural network or in a basic neural network, we might have 1, maybe 2 hidden layers. Most often, we've got multiple hidden layers. So we'll take this linear combination that's created in layer 1, pass it in through each of the hidden layers in layer 2, perhaps layer 3, perhaps more, to get our final output layer, which consists of the predictions. As we move through each layer or each step, the data is transformed. New variables are essentially being constructed throughout this process. These hidden layers you can think of as capturing those features that we really can't measure, and they do this through creating those linear combinations throughout. One downside to this approach is that it can be very difficult to crack those layers open, especially if we have many input variables that are being used to create many different hidden layers. It's difficult to truly get interpretable models out of these things. So that's why neural networks are often referred to as black box type models. We can use linear combinations or linear transformations. We can also use nonlinear transformations across each layer, meaning that we can get some very complex hierarchical relationships throughout this. There's a major cost to all of this. Neural networks, and especially deep neural networks, really are greedy. They need a lot of data. So if your number of observations is close to or less than the number of input variables, this really is not a good approach to take. You have to have a very large sample size to work with these. So that's the basic idea of a neural network. Let's talk about the feed-forward deep neural network, also called the multi-layer perceptron. So if you've heard that term before, this is the neural network architecture that's being used. Personally, I think this is a cooler name, but not as illustrative as feed-forward is. Here's the idea with these. Every layer in one of these neural networks is fully connected. What that means is that every variable inputs into every node in layer 1. Every node in layer 1 feeds forward into every node in layer 2, and so on and so on. So all of these are fully connected, and all of these are used in each successive layer. So we don't have any input variables that are coming in at layer 3, say later in the process. When we're building this structure of a feed-forward neural network, there are two things to consider. How do we decide how many layers to use? How do we decide how many nodes to use inside each layer? And then how do we deal with what's called the activation, or the change or calculation that's happening as we move from layer to layer? So let's talk about the layers and the nodes first. These are used to decide how complex the neural network needs to be. For most problems, you actually don't need that many hidden layers to do a good job. Something like 2 to 5 is often sufficient. Start somewhere in the 4 to 5 range. You can always delete layers if need be. The number of nodes in each layer is often equal to or less than the number of features that's being used. That seems counterintuitive, but it turns out that if you're training a deep model with lots of layers and fewer nodes, that can be more efficient than having fewer layers and more nodes. So sometimes it makes sense to have fewer nodes than your inputs. These output layers can predict really anything. We can predict a numeric output if we're doing regression. We can predict probability of success. We can predict multiple probabilities of class membership. We can take these probabilities that are being predicted and use them to classify then as well. So we can output numeric predictions, we can output classes, or we could output probabilities of class membership. For our problem, we want to classify observations as being 1 of 10 digits, so we'll use a classification type approach. So I'm going to start with just the default settings in this neural network, and then we'll see how to optimize it or how to modify it. So let's talk through how this works. The first model is using 2 hidden layers, one with 128 nodes. The second has 64 nodes. The final output layer has 10 nodes, 1 for each digit. So this is the first hidden layer right here. The first hidden layer needs to have the input shape argument. So that says how many features will be inputted into your data. For subsequent layers, you can decide how many nodes to include using this units function. So our first layer has 128 nodes. It's pretty big actually. Our second layer has 64 nodes. So we're trying to capture a lot of different features of this. This seems like a lot of nodes, but remember our original data has 784 input features, 1 for each pixel location in the image. So it's still a pretty sizable reduction. The last layer that we add is our output layer, and this should have the same number of nodes as the classification. So for example, if you were working with a binary classification problem, we would set this to be just 2. So then the compile statement comes next, and that's where you include your instructions for how to fit or how to optimize the model, and then how to evaluate the model. Compile has no defaults, so these must always be specified. The loss, the optimizer, and the metrics may change depending on the type of model that you're looking at. So let's actually run this first model over in RStudio Cloud. So I'm going to head back to my notes here. One warning that I've got for you guys. So as I fit these, there's kind of a cheat, essentially, that I have to do working in RStudio Cloud that you may not have to do in other libraries. Specifically, I have to actually specify my model twice. So I specify my model here. This is the code that generates that slide. Here, essentially, we have some messages saying that we are supporting some instructions. All of this is fine. Here, we'll run our model. So you can see in the output, our model's being compiled. So this is each call or each fit. You can see the loss or the information that we're losing decrease in live time or in real time. You can see the accuracy ideally increase in live time. While that's populating, unfortunately, to keep working with this model, the code specifying the model has to be directly following any interactions with the model. So as you'll see later on, notice this is almost done. I'm actually re-specifying the model each time I fit it in a code chunk. So that's something to keep in mind if you're running this in RStudio, specifying it here as well. So now looking at the loss function, it looks like our information that we've lost dropped down pretty significantly after the first call. However, our accuracy for classifying digits is only 21%. So that tells me that the default options are kind of junk. Looking at a plot of this model fit, so this is the same plot that was being generated live in the RStudio console. As we increase, say, the epoch that we're on, and we'll talk about what these mean pretty soon, the loss starts to level out, the accuracy starts to level out as well. So we're approaching some fit. It's not a good fit. To get the predictions from a neural network, we can use a function called predict_classes. So model 1 is my neural network, MNIST-X, this is my training data set. Here are the predictions on the training data set. We know what the first 6 observations are. We've viewed those before. We've got a 5, a 0. The 5th observation is a 9. That's the only thing that we've predicted correctly so far. Again, in RStudio, you have to keep all functions related to a keras model within the same chunk, or alternatively, you can redefine it. So my recommendation would be to write all of your code for this for a problem in one chunk, and then call back to different options or different parts of that chunk as you're writing your homework problem. I don't know exactly why this is the case, but if I had to guess, it would be that each chunk is calling Python in the background and then not remembering the calls that were sent to Python. So that's my hunch as to why this is happening. All right, so I'm going to stop this recording here. In the next video, which we'll pick up on the very next slide, we'll talk about some customization options. So this is part 1 of neural networks.